Hello, dynamics students. This mini lecture continues our discussions of rectilinear kinematics, particle kinematics. So we're again looking at something that we can consider a particle, maybe a body that we can just simply look at in terms of its center of mass, traveling in a straight line in the I hat, j hat, or k hat direction, only one. So we can focus on the magnitude of position, velocity, and acceleration because the direction of travel is not changing with time. Now, we could be having something that's moving in a positive or a negative direction, which is something that we can indicate with a positive or negative magnitude, but we're not having to look at any changes in our unit vector directions with time. Okay, so we're going to look at this example of a couple of masses. In this case, we've got our mass A hanging by a cable, which comes up over a pulley, and then it goes down underneath another pulley, and then it fastens to the ceiling here. And we've got another mass B that is hanging from the center of this pulley. Okay, so we can look now. We have three choices of reference frames. We can look at the mass A reference frame and how everything else is moving with respect to it. We can look at the mass B reference frame and look at how everything else is moving with respect to it. Or we can look the way we normally would look and take something that we presume is fixed, like the ceiling here, and say, okay, we're going to look at basically a vector direction, say j hat, which is up with respect to our ceiling in this case. So a reasonable reference frame that we're used to using that would include both of these masses would be the reference frame of the ceiling. So if we knew the rates and we knew the motion of both of these masses with respect to the ceiling, then we could look at how they move with respect to one another. So we could look at relative rates of A versus B. But one interesting thing to think about is if you were standing on mass A and you were standing still, mass A was standing still from your point of view, what would the whole rest of the system look like it was doing? So we're told the block A travels down at 3 times t squared, and the whole thing is in meters per second. Now, this is with respect to the ceiling reference frame, okay? And someone wants to know, what is the velocity of block B at t equals 4 seconds? Again, with respect to the ceiling reference frame. Now, let's take a minute before we start jumping into relative rates here. Effectively, block A is traveling down. If you were standing on block A, the ceiling would be traveling upwards at 3 t squared meters per second. And block B would be traveling who knows what relative to you. That's a little complicated. So just bear in mind, we can look at this now from multiple different reference frames, but we're going to pick the ceiling reference frame as our common reference frame. We're told what the velocity and initial position of A is. It's y, some y of A. We know what its velocity in the ceiling reference frame is. It's 3 t squared meters per second down. And someone wants to know, well, what about block B? What's its velocity in the C reference frame? Well, to solve this problem, we need to relate the rates. Basically, it's a related rates problem. So we've chosen our common reference frame. So we need to find some way to relate the rate we're given for the travel of block A to the rate of travel of block B with respect to our ceiling reference point, which we can denote as y sub c for effectively the position of block B, because it's dangling a negligible amount from the center of the pulley, versus y sub A, which is our position relative to our common external reference frame for A. And again, we have one direction. We have the j hat direction. We're moving in the positive j hat up towards the ceiling, or we're moving in the negative j hat down from the ceiling. So again, rectilinear. So we really only have to look at the magnitudes of these rates, which will include a sign. So how do we connect the rate at which A is moving in the j hat direction to the rate at which B is moving? We have to find a way to relate the rates, related rates problems. Well, we use the fact that they are connected by a string, which is not broken, is not breaking, and is not stretching. So that says that somehow the position of B and the position of A with respect to the ceiling and the length of this string has to, we have to be able to relate those together. So we say, okay, the length of the string, well, let's add it up. We're going to start the string at the ceiling. So we've got y sub c. Hey, no, that's a number we're going to need to know. That effectively is going to be the position of weight B. Okay, that's a good thing. So the position of weight B is contained somewhere within an expression for the length of the string, which is constant with time. Okay, now we've got to add half of the circumference of pulley C. Well, we're given the radius, so no worries there. So 2 pi r, half of that is pi rc. So we have y sub c plus pi rc. And then we've got whatever the difference is in length of the position of R, the center of the pulley D and the center of the pulley C. So we can relate that. We're given where pulley D is. It's fixed with time. It isn't moving anywhere. Pulley C is moving and weight A and B is moving, but D is fixed at K. So this little space between R sub C and center, pulley C center and pulley D center is just basically y sub C minus K. So we got a y sub C plus pi r sub C plus y sub C minus K, which brings us to here. Now we got to add half the circumference of pulley D. So we've got pi r d, and then we can add to that y sub A minus K for this remaining length, and we've added up the full length of the string. And in so doing, we have expressions for the things that are moving, our two positions. Okay, what does this have to do with relative reference frames? We are expressing everything we care about, positions and velocities, in a single reference frame. And in so doing, we can get expressions for them relative to one another. So you can think of the length of this string as being kind of like a coupling expression for the reference frame that contains the motion of each of these weights, their reference frames, to the reference frame of the ceiling. We can relate everything through the length of that string. Okay, so we're going to write out the tally up of the length. We've got y sub c, then half the pulley circumference of pulley C, plus the distance, the vertical distance between the centers of pulley C's and D's, half the circumference of pulley D, and then the tail from that edge of pulley D, tangent to pulley D, and then down to weight A. So L is constant, string's not breaking or stretching. We got a position with respect to the reference point, to the ceiling of pulley C, which effectively contains the position of weight B. We're going to assume y sub c is the position of weight B. So that would be like R0 to B, position vector. Pi rc isn't changing. The pulley's not changing size. We've got our position again, minus a constant, because pulley D is not moving anywhere. It's independent of time. Its radius, pulley D radius, is independent of time. And now we have the position of weight A, which is time dependent, minus another constant. So we have our two positions of interest, and everything else in this expression is a constant. Booyah! Okay, that's really good. And this is all, we were able to obtain this expression by plopping the two positions of interest into a common reference frame. Great. But we cared about velocity. Easy peasy. Take the first time derivative. We're not changing direction. Everything on this line could have an honorary j hat associated with it. In fact, I might ought to have included that. But because everything in this problem is automatically in the j hat direction, that was basically implied here with our rectilinear motion. So let's just go ahead and take the first time derivative. Time derivative of L is a constant, so first time derivative is 0. First time derivative of y sub c is y dot c. Ooh, that's the rate of change of position of weight b. That was something we wanted to know. So this is actually a thing we'll be solving for. Time derivative of another constant is 0. And in this expression, we got one constant, and then we're going to have the time derivative of position for weight b, which is the rate of change of this distance again. So we've got another y sub c dot. Derivative of constant is 0. And now we have the velocity of weight a minus k, and k is also 0. I could have written that 0. Okay. So if we group all the terms, we end up with 2 times y dot c, so 2 times the velocity of b, otherwise known as the time rate of change of this distance is effectively the velocity of weight b, plus y dot of a, the rate of change of this distance is the velocity of weight a descending. Those are equal. So I can relate those two. So I can say the velocity of block B is negative 1/2 times the velocity of weight A. So they're going in opposite directions. That's what this negative sign says. So if weight A is going down, weight B is going up. They're going in opposite directions. So I was given a time-dependent expression here for the velocity of weight A, and I was told that denotes the downward direction. So negative downward direction means upward direction. So negative 1/2 3t squared, where I guess I could call this positive. We've got weight A would be effectively positive in this case, 3t squared. And then so I end up with a y sub c being negative 1.5 t squared, meaning opposite downward, upward direction. So if I put in 4 seconds, I can say that y sub c dot is negative 24 meters per second, meaning upward, opposite of the effectively positive 3t squared. So if I wanted an expression for the distance between the blocks, which might be a starting point if I were going to say, well, if I were in reference frame A, how fast would B be moving towards me or away from me in the j hat direction? I would just subtract this rate from the rate of block A at the same time mark. So at 4 seconds, block A is traveling downwards at 48 meters per second, 3 times 16, and block C is moving upwards at 24. So 48 and 24, add those, so the relative rates, effectively, if you were standing on block A, block B would be zinging upwards at a rate of 48 plus 24 meters per second away from you. So it would be moving upwards very fast relative to you. Relative to the ceiling, it's moving upwards at 24 meters per second. So That's an example of using a common reference frame, rectilinear kinematics, to relate the rates of two different objects that are moving within that reference frame. And this time we related the rates by the fact that they were connected by a non-stretching string. And we could use some geometry. Okay, so now we can use a little more geometry. Here's another example. You've got a lamp 16 feet high, and you've got a fellow walking away from the lamp. He's 6 feet tall, and his shadow is being cast out in front of him as he walks. So he's walking along the sidewalk in the positive x direction. So it looks like this is a 2D problem. But really it's a 1D. It's a rectilinear kinematics because the only motion we care about is in this x direction. So effectively it's an all I hat problem. Things that are happening in the j hat direction, we're only going to use those to establish some geometric relationships for things in the I hat direction. But nothing, notice the lamp is fixed, its height is fixed, the man's height is fixed. Nothing's changing in the j hat direction. So things in the j hat direction merely establish relationships between the rates of change in the I hat. So another related rates problem. So let's look at the first rate. Let's look at the rate that the man is walking along the sidewalk in the positive I hat direction. He's going at 4 feet per second. So that's rate number 1. Someone wants to know what is the speed of the man's shadow with respect to the ground. Okay, so the 4 feet per second that the man is walking along the sidewalk is referenced to the ground. Okay, and we're looking at the speed of the man's shadow would be basically this leading edge of the shadow. So where's the leading edge? Well, it is defined as basically the intersection point of a line that attaches the lamp and the man's head. It's going to fall on the shadow. So that's kind of a physics ray diagram kind of consideration. So basically his shadow edge is going to be defined by these right triangles. So the height of the man, the length of his shadow, that relationship is going to be the same as basically the shadow distance plus the man's position relative to the lamp and the reference to the height. So we've basically got a couple of similar triangles. The total lamp height and the total combined position of the man plus his shadow versus just the man and his shadow. Okay, so those are gonna be common, basically. Similar ratios. So that's going to give us a way to relate those rates together. So notice what we have expressions for are not velocities but positions. So we can relate the positions relative to the ground. So we could look at a reference frame of the man, and we could imagine he's still, and the lamp is moving backwards behind him, and his shadow is extending out in front of him as this angle gets shallower and shallower. He's just standing there, and his shadow is just growing out in front of him. That's what you might see from the man reference frame. From the shadow reference frame, that's a little harder to imagine, so I won't go there. But we're looking at the common reference frame of the ground, which is a lot easier to envision. So we're going to look at relating position and velocity of the man and the shadow, meaning this leading edge, with respect to the ground. So position is time dependent. Guy's walking forward. Shadow position is probably going to be time dependent too because it is related by these similar triangles. So let's look at that relationship. we can draw the triangles out. So we have the man's height, basically 6 feet, his position, x sub m here is going to be related to this part of the triangle, or times 16 feet, the same way that the shadow position is going to be related to the remainder of that height, 10 feet, both reference to ground. So this expression is coming out of our similar triangles geometry. So you've got the whole x sub s versus the 16 feet versus just the man's 6 foot height and his distance. So those are the two relationships that we have. So from that we can get basically an expression relating the man's position, the shadow's position. So here we go. This is even simpler than our cable length. So we have the whole length x sub s, which is basically the leading edge of the shadow's position. We're not looking at the length of the shadow. We're looking at the whole, basically the whole the distance from the lamp to the leading edge is 8/5 times whatever position distance the man is from the pole. Okay? Those are both position expressions with reference to the ground reference plane. How do I get velocities? How do I get speeds in that positive, I hat direction? First time derivative. So x shadow dot equals 5/8 xm dot. And xm dot, the time rate of change of position of the man is 4 feet per second. So I can just multiply 4 feet per second times 8/5. I get 6.4 feet per second versus the ground, because 4 feet per second was versus the ground. So if I want to get the shadow's position at any time, basically, or it's the shadow length, I can subtract this point versus the man's point and get an expression for the lengthening of the shadow itself at 2.4 feet per second. So that's another example of using relative rates of change that we can get from some geometry or the physics of the problem. In the case of the pulley, we had the two positions of the weights being related by the length of the non-stretching string. In this case, we have positions, the length of a shadow or the position of its leading edge being related to the speed of the person casting it, being related by the geometry of that person's height versus the lamp, and similar triangles. And then basically expressing everything in terms of a single common reference frame that both are moving with respect to. And then take the first time derivative, relate the rates. Okay. So we have a final example here of particle kinematics that I'll discuss today, and just walk through this very briefly. This might be a really good one for you all to practice with. This is the same kind of consideration. There's a lot of geometry here, so I'm just going to set this up for you and invite you to walk through the rest of it. If you're taking this course and looking at this video, you can either take a pause and scroll through the rest of the notes. If you have access to all of these notes, of course, you can use them for reference. So I'm going to scan out a little bit. No, that's a little bit illegible. I'll scan down so you can see all of it. But this time we have, again, we have rectilinear motion in the I hat direction, and this is at a slope. So since we're in kinematics, not kinetics, we're not going to be looking at forces of gravity and resolving forces into the x direction, to the parallel to the slope and normal to the slope, although presumably that has been done. And as a result of that analysis, somebody figured out that the acceleration of this cart A is 2 meters per second squared upslope. Maybe it's being propelled by a motor. And the velocity at 0 time, at t equals 0, is 2 meters per second. So it's accelerating at 2 meters per second squared upslope in the positive I-hat direction, and we have an initial condition of velocity at t equals 0 of 2 meters per second. So 2 and 2. The cord won't stretch, so we've got like a cable, and it's connecting another cart through a frictionless pulley to like a little weight or a rock that's sitting on top of cart D. So you know, the little rock B, it can move across the surface of the cart D, and if it moves more than 1 meter from its current position to the edge of D, it'll fall off, which might be bad. So presumably we're trying to keep that from happening. So the cord isn't going to stretch, so basically we can, because the cord won't stretch, we can relate the rate of position change relative to the ground of B and D and A. All relate. Now we got 3 things. We're going to relate those rates to a common reference, and then we're eventually going to want to relate through that position of B and D, because we're going to want to know when B falls off. So we're told the point D here, where we've got the cable attached, has a constant velocity upslope. So velocity is changing with time of point A. Point D is moving upslope at a constant velocity, and point B is related to both A and D by the string length somehow. So we want to know when B falls off. So a handy-dandy way to do that is to create expressions for position and velocity and acceleration of all of our 3 bodies of interest, A, B, and D. Pretend they're all particles, with the exception of D, which we're going to kind of look at as a particle at this one point, because we really don't care about the rest of it. We really only care about this 1 meter separation. So we really don't care that it's a cart that has big volume. We can kind of look at D as a single particle at this point D. Cart D is really point D. Our little block B, we don't care how high it's sitting up. We just know that it's starting 1 meter downslope of point D, and when it has the same position relative to the slope as D, something falls off. So we can treat B and D as particles. We can treat A as a particle sitting at the center of the pulley. So if we knew the position, velocity, and acceleration of all 3 particles with respect to a common reference frame, then we could relate their rates to each other, and we could see when the position of point B and point D were like the same, because that's where B falls off of D. So kinematics, we want a time-dependent expression for each of those 3 things in the I-hat direction relative to the ground. Now we could look at relative to each other once we do that, but all of our starting conditions are relative to the ground. So one common reference frame, we're going to write what we can about rates, positions, velocity, accelerations, everything we know about the motion of each of these things relative to the ground. Once we know that, then we can look at them relative to each other. So we can just go ahead and start with what we know about A. Well, we're given acceleration. Cool. Let's integrate that with respect to time, and we'll get velocity. So velocity for point A is 2t plus some constant. we'll use our initial condition of 2 meters per second to solve for the constant. So our velocity of the cart A, and more importantly point A right here in the middle of that pulley, is 2t plus 2 meters per second squared, or excuse me, per second in the positive I-hat direction. Everything's in the positive I-hat direction. It's rectilinear motion. Great. So I can integrate again and say the position of point A at any time is going to be 1/2 t squared times 2, which is t squared, plus 2 meters per second t plus another constant, which I don't know at this point, and it'll be in meters. Okay. Well, at least I've got an expression for velocity. Okay, how about D? It doesn't have any acceleration because it has constant velocity. And we were told it was a constant positive velocity of 1 meter per second. So its position at any time is just going to be a linear function of time. And we don't know where it started, so we got another constant. But if we knew what these two constants were, we could solve for the position of A and D at any time. And we might be able to do that possibly via some expression for the string length. I don't know. So, speaking of which, use string inextensibility. String's the same length. So what does the string connect? It connects B and D through A. So I should be able to relate the position of B, the position of A, and the position of D, all three of them, in some fashion or another by basically adding up everything with respect to those positions and adding it all to the string length. All right, so we're just going to kind of start at point D, and we're going to add up to the string length. So if we go from D to A, XA minus XD is this length right here. Then I'm going to add a pi r to go around the pulley up to here. And of course, that's constant. R is not changing with time. The pulley's not getting any bigger or smaller with time. And then we have XA minus XB completes this length. So there's the whole length of the string. It's not changing one bit. Okay. So I can combine like terms. So I get 2x sub A minus xd minus xb. Look at that. All three positions in one expression plus half the circumference of the pulley is the non-changing length of the string. Wow, it's not changing with time. Let's take the first time derivative, get rid of that constant we don't know. So if we do that, we end up zeroing out length. We get 0 for pi r because the pulley's not changing with time. So now we have a 3-variable in one equation expression relating the rates of change of position, so velocities. So 2 times x sub A dot minus x sub D dot minus x sub B dot, so velocity of A, velocity of D, velocity of B, they all add up to 0. Well, I've got an expression for velocity of A, and I've got an expression for velocity of D. How handy. So I can put those in, and because I got those two, I automatically have a nice expression for the velocity of B. And if I take the first time integral of that, I can get the position of B at any time. Well, that's nice. Position of B at any time is what I need because I need to know when B, its position is going to be 1 meter further over than it was to start with. Speaking of starting, I've got another constant of integration here, C4. So to get the position of B relative to some absolute, reference point here somewhere on that that I-hat axis relative to the ground. We haven't even defined actually a 0 point on the ground. So far we've kind of been working with everything relative. We may be able to invoke another initial condition. So let's go ahead and do that. We're kind of working with a lot of relative initial conditions. We do know that at time 0, the position of point D minus the position of point B is 1 meter. So we have relative positions. So we've got a relative initial condition. So we're going to have to somehow wrangle those around so we can come up with this C4 and get a solution that makes sense for what we need to do. Well, what we can do is go back to our position expressions for D and B and use this information and basically solve for that C3 and C4 together. So let's write what we know for our expression for position of point D at any time, and that's up here. That's that T plus C3 in meters. That's that constant of integration minus this expression, our 2t squared plus 3t plus C4. That's position of B at any time. And if t equals 0, that difference is 1 meter. Well, when t equals 0, everything goes to 0 except the constants. So that gives us a C3 minus C4 equals 1 meter. So we can add that in to our expression, and we can get an explicit expression for the relative positions of B and D, which really, as much as it would have been nice to have some absolute position for B, I don't care when B necessarily gets to any point relative to the ground. I care when it gets to 1 meter relative to D. Well, that's what I happen to have here. And that's really even better. So now we switch kind of from an absolute reference frame with a ground to really wanting to know something about relative reference frames between two moving bodies. So we kind of did a little switching of reference frames from, first I want to express all the positions and velocities with respect to the ground reference frame. Then I found that it didn't quite give me everything I needed, and I said, well, what I really need is something that is expressed in terms of reference frame of D versus reference frame of B. And that's what I ended up getting with this expression here. I said, what I really want is something in the D or B reference frame, and then what's happening to the other with respect to it. So I kind of switched reference frames when I invoked this expression in a way. I said, I really don't care where x sub B and x sub D are relative to the ground. I care where they are relative to each other. So that gave me the expression for the difference. And I could say, well, when is that difference 0? Well, when this expression is 0. And so I can use the quadratic formula and say that when t equals 0.366 seconds, this expression is 0, and therefore the difference in position of B and D is 0, and block B falls off the card. So again, rectilinear kinematics, we got one direction that we care about, one unit vector direction, in this case I-hat. It's not changing with time. All we're dealing with are effectively the scalar magnitudes of acceleration, velocity, and position of everything within that. We start out with everything referenced to a common reference frame that is outside of any one of the particles. The ground is our common reference. We get position and velocity expressions for everything we have. We input all of our given velocities, accelerations, all of our given initial conditions. And we say, now we need to switch over to another reference frame. Let's look at reference frame of B with respect to D, or D with respect to B. Express that difference and go, aha, that's what I really need to know. And we can use our final initial conditions for those relative positions to get what we really needed. So lots of concepts being combined into one problem. But basically, first concept, rectilinear kinematics. Direction isn't changing with time, only magnitudes. We're relating time derivatives and integrals of acceleration, velocity, and position. And then we're switching between different reference frames to express the motion of different things we care about and relate them together by some physics that we know in the problem. And again, this time it was another non-stretching, non-breaking string. Okay. So we are going to stop the lecture at this point, and we're going to pick up again with a curved path and then launch into cylindrical coordinates, which is the first time where we're going to encounter a unit vector which is not necessarily constant with time. But that's okay, because it's worth being able to go in a curved path.